From its perch about 1 million miles from Earth, James Webb has captured extraordinary shots of our solar backyard, while also peering deep more than 13 billion years into the past, at an era when some of the first stars and galaxies were taking shape. But as James Webb delved deep into the first chapter of the cosmic history book, it found unexpected shreds of evidence that shake our cosmology. Look at unprecedented images of the early universe taken by James Webb. Nobody can still hold on to old theories and claim that they are still true. Webb's discoveries present a serious challenge to our best model of how the cosmos evolved. But is the standard model of physics now broken? Join us as we dig deep into how James Webb's view of the ancient universe just shatters our basic understanding of the cosmos. The first billion years of the universe's life were a crucial period in its evolution. In the first moments after the Big Bang, matter and light were bound to each other in a hot, dense soup of fundamental particles. However, a fraction of a second after the Big Bang, the universe expanded extremely rapidly. This expansion eventually allowed the universe to cool enough for light and matter to separate out of their soup and, some 380,000 years later, form hydrogen atoms. The hydrogen atoms appeared as an intergalactic fog, and with no light from stars and galaxies, the universe was dark. This period is known as the Cosmic Dark Ages. The arrival of the first generations of stars and galaxies several 100 million years after the Big Bang bathed the universe in extremely hot UV light, which burned or ionized the hydrogen fog. This process yielded the transparent, complex, and beautiful universe we see today. Astronomers call the first billion years of the universe, when this hydrogen fog was burning away, the epoch of reionization. To fully understand this time period, we study when the first stars and galaxies formed, what their main properties were, and whether they were able to produce enough UV light to burn through all the hydrogen. The first step toward understanding the epoch of reionization is finding and confirming the distances to galaxies that astronomers think might be responsible for this process. Since light travels at a finite speed, it takes time to arrive to our telescopes, so astronomers see objects as they were in the past. For example, light from the center of our galaxy, the Milky Way, takes about 27,000 years to reach us on Earth, so we see it as it was 27,000 years in the past. That means that if we want to see back to the very first instance after the Big Bang, we have to look for objects at extreme distances. Because galaxies residing in this time period are so far away, they appear extremely faint and small to our telescopes and emit most of their light in the infrared. This means astronomers need powerful infrared telescopes, like Webb, to find them. Prior to Webb, virtually all of the distant galaxies found by astronomers were exceptionally bright and large, simply because our telescopes weren't sensitive enough to see the fainter, smaller galaxies. However, it's the latter population that are far more numerous, representative, and likely to be the main drivers to the reionization process, not the bright ones. So, these faint galaxies are the ones astronomers need to study in greater detail. It's like trying to understand the evolution of humans by studying entire populations rather than a few very tall people. By allowing us to see faint galaxies, Webb is opening a new window into studying the early universe. Early galaxies were not like those we know today. The first galaxies were more pristine, composed primarily of hydrogen and helium gas. Over time, their stars would fuse atoms to form heavier elements, and when these stars died in supernova explosions, the heavy elements dispersed throughout the galaxies, enriching them with star stuff, including the elements needed to create life. The first galaxies had yet to settle into majestic spiral patterns or puffy elliptical balls like the galaxies we see around us now. They were far more disordered and much smaller, making them even harder to find. The earliest galaxies we have seen were about 1% the size of our Milky Way, but they were growing rapidly, forming new stars at prodigious rates. Fuel was plentiful back then, Early galaxies were bathed in cool streams of flowing hydrogen gas, lured inward by gravity. The galaxies collided with one another and merged frequently, accelerating their growth and triggering new bursts of star formation. As the universe expanded over time, galaxy growth slowed, significant mergers became less frequent, and the gas supply thinned out. This picture is our basic understanding of cosmic history. We are still working to fill in the details, and many questions remain, especially surrounding the earliest times. When did the first galaxies form? How small were they? What did they look like? Were they building blocks of galaxies to come with single large regions of star formation? Or were they more fragmented and clumpy? Were they all bursting with intense star formation? Or were some more relaxed, like most galaxies today? Did any early galaxies have time to settle into disks like the Milky Way did? Or were they merging too frequently to do so? Will we ever find any filled with pristine hydrogen and helium gas? Or did the first supernovae enrich them too quickly with heavier elements? How rapidly did early galaxies build up in mass and numbers? And were they in fact responsible for reionizing the universe? With the results from James Webb, we are taking another step toward answering these questions. Thanks to its infrared eyes, James Webb is adding a bounty of distant galaxies beyond Hubble's reach and revealing the early universe in far greater detail than previously possible. Webb's images of the early universe have acted like an ocean swell, delivering new waves of evidence. A new research using the James Webb data found that dwarf galaxies in the early universe often look flat, either prolate, elongated along one axis, or very narrow oblate ovals shaped like a surfboard, whereas others have a more frisbee-like oblate appearance. These galactic frisbees seem to grow more abundant as the universe ages, as do the compact, spheroidal-shaped galaxies. As Viraj Pandya, a Columbia University astronomer and lead author of a new paper describing the research, said in a press statement, roughly 50 to 80% of the galaxies we studied appear to be flattened in 2 dimensions. They seem to be very common in the early universe, which is surprising since they are uncommon nearby. The discovery was made using data from CEERS, or Cosmic Evolution Early Release Science, a James Webb program to push back the veil and probe the lives of the oldest, faintest galaxies in the universe. It's an era spanning from 600 million years after the Big Bang to 6 billion years later, during which the galaxies that we see in the universe around us today formed, evolved, and matured, from spirals like the Milky Way and the Andromeda Galaxy to giant ellipticals such as Messier 87. CEERS builds on previous work by the Hubble Space Telescope, which studied the early universe in its deep field images and its Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey program. Hubble found that massive galaxies in the early universe tended to take on the form of oblate spheroids, not dissimilar to the elliptical galaxies of today. Less massive and hence fainter galaxies were more difficult for Hubble to detect, but from what it could see, many of them took on an elongated appearance consisting of chains of brighter blobs, whereas other irregularly shaped dwarfs were nicknamed tadpoles, nuggets, or clumps. The question was, given Hubble's limitations, was it seeing a true reflection of the shapes of smaller early galaxies? The short answer is yes. James Webb's greater vision has now found that Hubble's earlier discoveries hold true. Karthik Iyer, also of Columbia University, described how the greater vision and sensitivity of James Webb, compared to Hubble, is changing the study of galaxies in the early universe. Identifying additional categories for early galaxies is exciting. There's a lot more to analyze now. We can now study how galaxies' shapes relate to how they look, and better project how they formed in much more detail. A picture now emerges of how galaxies may have evolved and grown over time. Matter is distributed throughout the universe primarily in a cosmic web of filaments that span the cosmos. These filaments are predominantly formed from dark matter, with a fraction of normal matter mixed in that forms the galaxies that we observe. The abundance of surfboard-shaped prolate galaxies could be explained by them forming inside halos of dark matter that are elongated in alignment with their cosmic Webb filament. Since other dwarf galaxies would also be forming within that filament, mergers would take place along it, leading to the growth of elongated galaxies that look like chains. Across billions of years, the cosmic Webb filaments disperse and grow more diffuse. The merger rate slows down, and the fraction of prolate galaxies decreases as they start to spin and adopt a disk-like, oblate structure. Such oblate galaxies are seen to increase from 20 to 60% over time and for a given mass of galaxy. Similarly, spheroid galaxies also grow more abundant over time, as compact star-forming galaxies in the universe settle down to become the progenitors of the giant elliptical galaxies we see today, or the spheroidal bulges of massive spiral galaxies. Understanding the evolution of galaxies over cosmic history is a key objective of James Webb. The new findings from SEERS indicate that hierarchical mergers, smaller galaxies merging with larger ones, along the aforementioned cosmic filaments, are key to understanding these varied galaxy shapes. But in addition to its stunning pictures, the Webb telescope has also pinpointed puzzling views that were impossible with previous telescopes. For instance, the telescope has spotted several galaxies in the early universe that appear to be utterly gargantuan, with masses ranging from 10 billion to 100 billion times that of our Sun. Put simply, these galaxies shouldn't exist according to rules laid out in the Standard Model. In other words, Webb's discoveries are stress testing the Standard Model of cosmology, also known as the Lambda Cold Dark Matter Model, exposing an important unresolved issue with the properties of galaxies derived from the observations. As Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, said in an email to Motherboard, "The results have been a real surprise for me, and it's been a very exciting period. I have never seen anything like the frenzy of activity and results that accompanied the release of the first data. Indeed, images captured by James Webb are jaw-dropping on a pure aesthetic level, but Boylan Colchin and other scientists have also found many riddles in the telescope's observations, including those massive galaxies that appear some 500 million years after the Big Bang. These objects really do appear to be early behemoths. They are so massive that we do not expect to have enough collections of atomic matter in the universe at that time to give rise to that much stellar content. So how did these galaxies get so big so fast? Webb's observations suggest that the answer may be linked to the rapid growth of supermassive black holes during the same time period. Virtually all modern galaxies contain a supermassive black hole at their centers, including the Milky Way, suggesting that this is a core feature of large galactic structures. If black holes in the early universe were able to grow to huge masses in a short time frame, it might explain why so many massive galaxies are showing up in the telescope's images. However, this explanation essentially trades out one mystery for another. As Boylan Colchin explained, if it does turn out that massive black holes are making these galaxies appear more massive than they truly are, then we will have other puzzles to understand. How did so many black holes grow so massive so quickly in the early universe? On the other hand, it's also conceivable that some unknown mechanism in the early universe supercharged the process of star formation, which could explain why these early galaxies appear so massive and bright. Another mind-boggling possibility is that these galaxies are packed with a group of stars called Population 3, which are the first stars that ever shone in the universe. Spotting these stellar ancestors has been a major goal in astronomy for decades, but it's extremely difficult to see objects that are this far away in time and space. Population 3 stars are expected to be brighter and more massive than their descendants, which hints that they might be hidden away in the strange galaxies seen by James Webb. However, if none of these explanations ultimately fit, It may be time to consider whether these ancient galaxies have exposed a fundamental gap in our understanding of the universe. Perhaps the observations made by James Webb are telling us that our standard and very successful lambda cold dark matter model is incomplete, that we're missing a component. There are clues that this is the case. Calculations of the expansion rate of the universe based on measurements at early cosmic epochs don't agree with direct measurements in the local universe, for example. And some proposed solutions to this disagreement, which is called the Hubble tension, involve adding additional dark energy at very early times, only 50,000 years after the Big Bang. An interesting byproduct of these early dark energy models is that they predict faster evolution of structure and more structure at high redshift, which is exactly what would help explain the existence of these massive early galaxies. It is intriguing that a single solution might explain both of these observational discrepancies. In short, one thing is clear. Scientists have their work cut out for them in terms of unraveling the true meaning of these bizarre images. To that end, future observations can help to confirm that these galaxies really are that massive, and astronomers also plan to look at much bigger patches of sky to make sure they aren't seeing a fluke that is limited to one region. However, for now, we will all have to uneasily sit with the unexplained presence of these galactic giants at the edge of space and time. Meanwhile, in another observation made by the Hubble Space Telescope, astronomers have just discovered that the atmosphere of a relatively small planet outside the solar system is rich with water vapor. However, don't plan a vacation to this destination just yet. The planet's surface is hot enough to melt lead, meaning it's a steamy world inhospitable to life as we know it. More specifically, the team behind this finding says the extrasolar planet, or exoplanet, named GJ9872d, exhibits Venus-like temperatures of 752 degrees Fahrenheit or 400 degrees Celsius. But that doesn't make this discovery any less exciting. Though scientists have found water vapor in the atmospheres of many extrasolar planets before, the Hubble telescope's observations of this hot and steamy world, designated GJ9827d, represent the smallest exoplanet around which this vital element for life has been found thus far. As Laura Kreidberg, team member and director of the Max Planck Institute for Astronomy's Atmospheric Physics of Exoplanets department, said, "The discovery of water on GJ9827d is exciting because it's the smallest planet yet where we've detected an atmosphere. It pushes closer than ever to characterizing truly Earth-like worlds." Elsewhere, astronomers has just witnessed 18 ravenous black holes ripping up and devouring stars. This result, made by a team from the Massachusetts Institute of Technology, more than doubles the number of gruesome, star-shredding tidal disruption events seen in the local universe. The findings could help astronomers better estimate the number of tidal disruption events occurring across the universe, bringing the rate closer to theoretical predictions. Tidal disruption events occur when a star gets too close to a black hole, and the latter object's gravitational influence generates tidal forces in the star so great that the stellar body is stretched vertically while squashed horizontally, a process called spaghettification. The material from the star forms a flattened disk around the black hole, with some of it accreting to the black hole's heart, while other stellar matter is channeled to the poles by powerful magnetic fields and blasted out as near-light-speed jets. Previously, astronomers had believed that black holes rip apart and devour stars while blasting out highly energetic jets in galaxies that have recently undergone periods of intense starbirth called starbursts. However, this research implies tidal disruption events can occur across a wider range of galaxies and could help explain the extreme physics seen around such events. As Aaron Kara, team member and an assistant professor of physics at MIT, said in a statement, "People were coming up with very exotic solutions to these puzzles, and now we've come to the point where we can resolve all of them. The MIT team began searching for more star-devouring black holes after they discovered the closest tidal disruption event to Earth ever seen. It was witnessed in the form of a flare from the galaxy NGC 7392, located around 137 million light-years from Earth. This opened up an entirely new way to spot actively feeding black holes, they said. It involves using infrared light and an algorithm that hunts for patterns in infrared data that indicate brief or transient bursts of radiation. The technique completed was based on historical data collected by NASA's Wide Field Infrared Survey Explorer, or NEOWISE for short. Since its launch in 2009, NEOWISE has been searching the sky over Earth for brief bursts of infrared light. The team then cross-referenced the transients they found with a catalog of galaxies within a distance of 600 million light-years of Earth, revealing that the infrared bursts could be traced back to about 1,000 galaxies. Zooming in on these galaxies, the researchers attempted to discover if the signals they had detected came from tidal disruption events, or if they could have been triggered by other violent events, such as the supernova explosion of a massive dying star. It'd also have been possible for them to come from supermassive black holes at the hearts of galaxies as they feed on in falling dust and gas. This ultimately led to the discovery of 18 legitimate tidal disruption event signals that were the result of the gravitational influence of black holes generating tidal forces in stars that eventually led to some gory stellar deaths. Surprisingly, the team found that tidal disruption events seem to occur across a range of galaxies across the entire sky, including ones that are filled with thick clouds of dust. According to research lead author and MIT's Kavli Institute for Astrophysics and Space Research graduate student Megan Masterson, if you looked up in the sky and saw a bunch of galaxies, the tidal disruption events would occur representatively in all of them. In the grand scheme of things, this research helps settle some major questions surrounding tidal disruption events. Previously, astronomers had mainly seen these star-shredding occurrences happening in post-starburst galaxies with stellar factories that had recently shut down. Such galaxies are fairly rare, and scientists were confused as to why tidal disruption events seemed restricted to them. This research alleviates that confusion by finding gory tidal disruption events in a spread of galaxy types. The reason tidal disruption events were seemingly absent from other galaxies is that, whereas post-starburst galaxies are devoid of thick gas and dust because they exhausted the materials, while creating a wealth of new stars, other galaxies still have the material in abundance. Gas and dust are adept at absorbing or blocking optical and X-ray light, but infrared slips through the matter more easily. Thus, X-ray and optical emissions were fine for spotting tidal disruption events in dust-depleted galaxies. But infrared observations were key in finding star-shredding black holes in dusty galaxies. It's not that they're only occurring in one type of galaxy, as people thought based only on optical and X-ray searches. If you want to understand tidal disruption events as a whole and use them to probe supermassive black hole demographics, you need to look in the infrared band. The findings from the MIT researchers could also explain why tidal disruption events don't seem to radiate as much energy as is predicted by theory, with the team suggesting that the energy deficit is the result of dust-absorbing optical and X-ray emissions, as well as extreme ultraviolet radiation from tidal disruption events. Adding the 18 new tidal disruption events they discovered to previously observed events of this nature, the MIT team estimates that galaxies experience a tidal disruption event roughly once every 50,000 years, which is in line with previous theoretical predictions. As Kara concluded, this gives us confidence that we don't need all this exotic physics to explain what we're seeing, and we have a better handle on the mechanics behind how a star gets ripped apart and gobbled up by a black hole. We're understanding these systems better. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. There was a time when people believed the universe to be a static space. Albert Einstein, even after revolutionizing his theory of general relativity in 1915, still thought that the changing size of the universe was impossible. However, in 1929, a young man named Edwin Hubble emerged. Whether you know about him or not, you've probably heard of the telescope named after him. Hubble wasn't the first to propose the idea of an expanding universe, but he is credited with proving it through his observations. Moving beyond that issue, what we are facing today are differing figures, depending on how we calculate the value of the Hubble constant from both nearby and distant data, as well as old and new. Measurements based on recently observed objects, astronomically speaking, such as supernovae and variable stars, yield a Hubble constant value of about 73.5 km per second per megaparsec. Meanwhile, measurements from very distant objects representing the early universe yield a value of 67.7 km per second per megaparsec. With this difference, 73.5 is not equal to 67.7. To add further complexity, in recent years, a new technique has been experimented with, utilizing giant red stars. Measurements from this method yield a Hubble constant value of 69.8 km per second per megaparsec. Falling in between the two previous values has left both camps somewhat disappointed. So currently, we have three different values for the Hubble constant, each measured and calculated very accurately, and each with fervent supporters asserting the correctness of their measurements. Numerous scientific papers have been published on this issue, and sometimes the debates between the factions have become heated. But in reality, what situation are we facing? Initial information. If you've ever heard the siren of a police car change pitch as it moves towards you or away from you, then you've experienced the phenomenon of Doppler shift. The change in pitch is caused by the motion of the siren compressing sound waves as it moves towards you, increasing in frequency. Conversely, as it moves away, the sound waves become stretched out, lowering the frequency. Similarly, this phenomenon applies to light. When an object moves towards you, the light waves it emits will bunch up, and the wavelength will shorten, making the light appear bluer, known as blue shift. Conversely, when an object moves away from us, the light waves will stretch out, and the light will appear redder, known as red shift. As an object moves away from us faster, the light emitted from it becomes more redshifted. Edwin Hubble demonstrated that the light from galaxies farther away is more redshifted than from galaxies closer to us. This property implies that galaxies farther away are moving away faster. This is known as Hubble's law. Thus, not only is the universe expanding, but that expansion is also unstable and accelerating. Hubble determined that the universal rate of expansion is 500 km per second per megaparsec. This means that for every megaparsec, MPC, roughly 3.26 million light-years, you observe, the expansion rate increases by 500 kilometers per second. Additionally, it is universally agreed that the universal rate of expansion is a noteworthy concept, so we often refer to it as the Hubble constant. The law, the constant, the telescopes. Edwin Hubble left a significant mark on various aspects of the astronomical world, leading to many things being named after him. Edwin Hubble may have clarified that the universe is expanding at an accelerating rate, driven by the outward force of dark energy, even though he couldn't precisely measure the Hubble constant with his tools. Nowadays, we use various methods to measure the Hubble constant. Some measurements are made using data from the cosmic microwave background, the low-level radiation from the Big Bang. Using telescopes like WMAP and Planck, we can examine the magnitude of fluctuations in this radiation to estimate the Hubble constant. We can also consider observations from very distant sources to determine the distribution of matter when the universe was young, using tools like the Sloan Digital Sky Survey. Comparing how matter was distributed billions of years ago with how it is distributed now can help us understand more about the expansion of the universe. Although we have instruments to perform highly accurate measurements of the Hubble constant, these measurements still don't match up. This poses an intriguing puzzle for the astronomy community as they strive to gain a better understanding of our universe. The expansion of the universe. Astronomers using NASA's Hubble Space Telescope have announced that they have surpassed a crucial threshold in revealing the differences between two main techniques for measuring the rate of cosmic expansion. Recent research further reinforces the argument that new theories may be needed to explain the forces that have shaped the universe. Hubble's measurements indicate that the rate of cosmic expansion in the modern universe is faster than expected, based on how the universe appeared over 3 billion years ago. These measurements of the early universe come from the European Space Agency's Planck satellite. This discrepancy has been identified in scientific papers over the past few years, but it remains unclear whether the difference in measurement techniques is the cause or if the difference could be due to unlucky measurements. The latest data from Hubble lowers the likelihood of the difference being merely random to 1 in 100,000. This is a significant increase compared to the previous estimate, less than a year ago, which was about 1 in 3,000. The most precise measurements by Hubble to date reinforce the idea that new physics may be needed to explain the mismatch. The tension of Hubble between the early and late universe may be the most exciting development in cosmology in decades. Lead researcher and Nobel laureate Adam Rees of the Space Telescope Science Institute, STSCI, and Johns Hopkins University in Baltimore, Maryland, stated, "This mismatch is growing and has now reached a level that can't be dismissed as a fluke. This discrepancy cannot occur randomly." Scientists use the cosmic distance ladder to determine the distances of objects in the universe. This method relies on making precise measurements of distances to nearby galaxies and then moving on to galaxies farther and farther away, using their stars as milestone markers. Astronomers use these values along with other measurements of the redshift of galaxies as they pass through an expanding universe to calculate how fast the universe is expanding over time, a value known as the Hubble constant. Ras and his ICS-UVUIS supernovae H0 for the equation of state team have been on a mission since 2005 to fine-tune those distance measurements using Hubble and refine the Hubble constant. In this new study, astronomers used Hubble to observe 70 moving stars called Cepheid variable stars in the Large Magellanic Cloud. The observations helped astronomers reconstruct the cosmic distance ladder by improving the comparison between those Cepheids and their more distant cousins in galaxies containing supernovae. Rees's team reduced the uncertainty in their Hubble constant value to 1.9% from the previous estimate of 2.2%. Astronomers have been using Cepheid variable stars as cosmic yardsticks to measure distances between nearby galaxies for over a century. However, attempting to harvest a series of these stars is time-consuming to the point of nearly being impractical. Therefore, the team has employed a clever new method called DASH, drift and shift, using Hubble as a point-and-shoot camera to quickly capture images of the extremely bright moving stars, eliminating the need for time-consuming precision. Stefano Casertano, a team member, explains, "When Hubble uses precise positioning by locking onto guide stars, it can only observe one Cepheid in each 90-minute Hubble orbit around Earth. So it would be very costly for the telescope to observe each Cepheid individually. Instead, they search for groups of Cepheids close enough together that they can move between them without having to realign the telescope's direction. These Cepheids are very bright, so they only need to observe them for 2 seconds. This technique allows for the observation of a dozen Cepheids throughout an orbit. So, we continue to spin the roulette wheel and keep running around very quickly. Subsequently, Hubble astronomers combined their findings with a series of observations conducted by the Araucaria Project, a collaboration between astronomers from organizations in Chile, the United States, and Europe. This team measured distances to the Large Magellanic Cloud by observing the dimming of light as a star passes in front of its companion in eclipsing binary star systems. As the team's measurements became more precise, their calculations of the Hubble constant still conflicted with the expected values from observations of the expansion of the early universe. Those measurements were made by Planck, a tool mapping the cosmic microwave background radiation, the remnants left over from 380,000 years after the Big Bang. The measurements were meticulously calibrated, so astronomers cannot dismiss the discrepancy between the two results as errors in any measurements or methods. Both values have been tested in multiple ways. This is not necessarily a disagreement between two experiments. They are merely measuring two fundamentally different things. One is measuring how fast the universe is expanding today, as we see it. The other is a prediction based on the physical properties of the early universe and measurements of the rate at which it should expand. If these values don't match up, there may be something missing in the model of the universe connecting these two eras. Early dark energy. The standard model of cosmology incorporates all known forms of matter and radiation, as well as their interactions. It also includes invisible substances called dark energy and dark matter, together making up about 96% of the universe. Because there is very little information about these dark components, they are perhaps the obvious place to start falsifying the standard model. The standard model assumes that dark matter consists of slowly moving particles that do not interact with light. But what if we also consider that dark matter is not just made up of a single substance? Since there exist various observed types of matter, quarks, electrons, etc., it is also conceivable that there could be multiple types of dark matter particles. In a paper published last summer in the journal Physical Review D, Loeb and two collaborators examined a form of dark matter decaying into a lighter particle, and a massless particle called a dark photon. They theorized that as more dark matter decays over time, its gravitational force would decrease, thereby accelerating the expansion of the universe and reducing the tension in the Hubble constant. However, implementing such small changes to the standard cosmological model could lead to unintended ripple effects. Mark Kamiankowski, a theoretical physicist at Johns Hopkins University, stated, "It's very easy to come up with all sorts of small modifications, but it's challenging to do so without disrupting the model's perfect fit with countless other astronomical observations. By adjusting the decay rate and the amount of dark matter lost in each decay event, Loeb and colleagues have identified a decaying dark matter model that they believe still fits with other astronomical observations." Loeb stated, "If you add this component to the standard model of cosmology, everything falls into place." However, he is still unsatisfied with the idea of decaying dark matter, partly because it introduces two new, uncertain quantities into the equations. Since the surprising discovery in 1998 that the expansion of the universe is accelerating, cosmologists have incorporated dark energy into their models of cosmic evolution. But its nature remains a mystery. The simplest possibility is that dark energy is a cosmological constant, the energy of space with a constant density everywhere. But what if the amount of dark energy in the universe is not constant? According to a new study by a group of astrophysicists, the existence of primordial dark energy may be the solution that cosmologists are seeking. The study was conducted by Mark Kamiankowski, a professor of physics and astronomy at Johns Hopkins University, JHU, and Adam G. Rees, the Bloomberg Distinguished Professor at JHU and the Space Telescope Science Institute, STSCI. Their paper, titled Hubble Tension and Primordial Dark Energy, is under review for publication in the Annual Review of Nuclear and Particle Science, ARNPS. In the paper, they explain that there are two methods for measuring the expansion of the universe. The direct method involves using supernova as standard candles, or distance markers, to conduct measurements on a local scale. The indirect method involves comparing measurements of the cosmic microwave background, CMB, with universe models, such as the lambda cold dark matter LCDM model, which includes the presence of dark matter and dark energy. Unfortunately, these two methods yield different results, with the former method yielding a value of 73 km per second per megaparsec, and the latter method yielding 67 km per second per megaparsec. Dr. Rees further elaborated on this matter in an email to Universe Today, stating, "The Hubble constant is the current rate of expansion of the universe. The Hubble tension is the difference in the value you find for the Hubble constant when you measure the current rate of expansion as well as possible, or predict the value it should have based on how the universe handles the Big Bang, combined with a model of how the universe will evolve. It is a problem because if these two ways don't agree with each other, it makes us think we are misunderstanding something about the universe." Late solutions suggest that the energy density in the universe after recombination, when the ionized plasma of the early universe formed neutral atoms about 300,000 years after the Big Bang, is lower than in the standard LCDM model. Meanwhile, early solutions suggest that the energy density somehow increased before recombination occurred, causing the sound horizon to shrink. For their research purposes, Kamiankowski and Keenan considered primordial dark energy, EDE, as a potential candidate. As Rice explained, the presence of EDE would contribute about 10% of the total energy density of the universe before recombination occurs. After recombination, the energy density will decay faster than other forms of radiation, thus leaving the late-time evolution of the universe unchanged. Rice stated, "It would create an unexpected burst of expansion in the universe that, if we didn't know about it, would make the predicted values lower than the actual ones." What makes EDE more favored than late solutions is that it implies the existence of a fluid generating energy from nothingness effectively, violating the strong energy condition that GR predicts. Furthermore, such models are very difficult to reconcile with measurements of the cosmic distance scale using Cepheid variable stars and type Ia supernovae in nearby galaxies, targets with low redshifts, and type Ia supernovae in distant galaxies, high redshifts. In summary, solutions related to modifications to the dynamics of the early universe seem to be the most compatible with the established cosmological constraints. Although there is increasing evidence suggesting the existence of EDE, our current measurements of the CMB are still not precise and powerful enough to distinguish the EDE model from the standard LCDM model. What is needed in the future are improved local measurements to refine the Hubble constant and eliminate any systematic errors. Secondly, more accurate measurements of CMB polarization at smaller angular scales are needed to test EDE and other new physics models. Modified gravity. In the standard model of cosmology, all known forms of matter and radiation, along with dark matter and dark energy, are incorporated into Albert Einstein's theory of gravity, and Einstein's equations dictate how space expands. This means that, besides modifying or supplementing the universe's components in the model, there is another way physicists can reconcile it with the observed rate of cosmic expansion. You can imagine that Einstein's equations are not correct. William Barker, a doctoral researcher at the University of Cambridge, began exploring a theory of varying gravity last summer when he stumbled upon a solution to the Hubble tension. Barker found a gravitational model that has been adjusted to act as if there were additional radiation in the early universe. However, in a preprint submitted to Physical Review D in March, Barker and 3 co-authors acknowledged that further analysis is needed to determine whether the model can describe not only how the universe expands, but also how structures like galaxies and clusters develop. Sergei Ketov, head of the Laboratory of Theoretical High-Energy Physics at Tokyo Metropolitan University and a visiting scientist, says, "There are many versions of modified gravity because it can be anything beyond Einstein's broad theory of relativity. Essentially, modified gravity assumes that at the largest and/or smallest scales, gravity behaves differently than at the meticulously tested scales in between, including the constantly explored scales of the very young." Ketov says, "There are now many reasons to expect modifications of the broad theory of relativity for both very large and very small distances." The reasoning behind this thought is that until now, as Ketov points out, we have only truly tested the theory of relativity with extremely high precision in our solar system. To name a few cases, we have evaluated how four-dimensional spacetime, as theorized, affects the orbits of planets, as well as the rotational motion of gyroscopes aboard satellites orbiting Earth. A series of upcoming experiments, some involving the Kavli Institute of Theoretical Physics, are aimed at expanding the testing of the accuracy of gravity beyond the much larger universe. There are currently quite a few important observational tests of modified gravity in the pipeline. They all relate to precise measurements of cosmic parameters involving inflation, dark energy, dark matter, and gravitational waves. When using the term inflation, Ketov refers to the theory that the universe underwent significant expansion in the very early stages of the Big Bang. This inflation is believed to leave traces in the remnants of light from the Big Bang, known as the cosmic microwave background radiation, which permeates space today. The BICEP 3 project is currently searching for these signatures using telescopes at the South Pole. Meanwhile, the Euclid Space Telescope, scheduled to launch next year, will accurately measure the shapes and distances of galaxies from Earth to rigorously test the push and pull effects of dark matter and dark energy. Other efforts include the detection of gravitational waves, ripples in the fabric of spacetime described by Einstein's theory of general relativity, first observed in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, a project led by members of the Kavli Institute for Astrophysics and Space Research at MIT. Two other gravitational wave detectors, Virgo and Kagra, have joined the effort. These experiments are raising hopes among modified gravity researchers that ultimate anomalies in the waves will appear, supporting models beyond Einstein's theoretical framework. A gravitational wave detector in space called LISA is also under development and promises even greater sensitivity. Regardless of any new insights that may emerge, Ketov points out that the theory of general relativity has been tested and found to be likely still part of a broader framework for what we call gravitational force. Ketov states, "Modified gravity doesn't exclude Einstein's theory, but it shows its boundaries." Fully understanding the nature of gravity will help us not only the origins and past of the universe, but also its future. We may conclusively answer whether the universe will continue expanding indefinitely or ultimately collapse back into a big crunch. More relevant to humanity at present, full computations of gravitational forces will enhance our understanding of fundamental physics. Conversely, this could pave the way for new technologies and capabilities vital for the existence and advancement of our species someday, perhaps across larger galaxies. With modern telescopes providing vast amounts of accurate data on such structures, devising a theory that fits all observations is no easy task. Many theories of modified gravity are not complete theories, and when you're trying to perform detailed calculations with complex data sets, it's challenging to do so conclusively. As the James Webb Space Telescope continues its cosmic odyssey, the images of distant galaxies and potential supermassive black holes stand as testaments to humanity's insatiable curiosity. The telescope's transformative capabilities not only captivate our imagination, but also provide invaluable data for scientists worldwide. These awe-inspiring images serve as a reminder that the universe is a vast, dynamic tapestry waiting to be unveiled, and the James Webb Space Telescope is our window to the cosmic wonders beyond. In the beginning, there was a bang. Big Bang, if you will. This massive explosion created the universe and filled it with the seeds of all the matter and energy currently present. But with that kind of turbo kickstart, growth isn't something that ends after the initial blast. The universe continues to expand, even accelerating as it goes, at a rate referred to as the Hubble constant. The Hubble constant is an incredibly important number to pin down in the field of cosmology, but it's not an easy one to suss out. In fact, it's so difficult to divine that the Hubble tension caused by our inability to land on a single number has become arguably as famous as the Hubble constant itself. And recent results from the James Webb Space Telescope have just re-cemented this tension as a very real problem to overcome. If a researcher wants to estimate the Hubble constant, they have two main avenues. There are others, of course, but the two most common are Cepheid variables and the cosmic microwave background. The cosmic microwave background is the leftover radiation still permeating the universe from the Big Bang. Using the cosmic microwave background is often likened by researchers to using a baby picture to predict what someone will look like as an adult. To some extent, knowledge about the universe's infancy should allow researchers to make predictions about its current state. Researchers have long used it to make inferences about the very beginnings of our universe, and have used it to predict what the Hubble constant should be. Fairly recent cosmic microwave background calculations set the Hubble constant at around 68 kilometers per second per megaparsec. But the thing about theory is that you need to test it, and when the Hubble telescope launched, it became possible to do just that. Free of the constraints of ground-based telescopes clouded by atmosphere, the Hubble telescope was able to take extremely accurate distance measurements of far-off objects. And that's where Cepheid variables come in. Cepheid variables are a type of pulsating star that falls into a category of objects called standard candles. Objects that have a measurable and consistent brightness, allowing us to fairly straightforwardly measure how far away they are. Measuring distances isn't easy in space, but it's crucial to being able to measure expansion. As convenient as it would be to stop there, there's one more step to the Cepheid method. Once their brightnesses have been divined and we know how bright a Cepheid is that blinks at a certain rate, we use those brightnesses to calculate the brightnesses of nearby supernovae. Then, using a quality called redshift, we use those supernovae to calculate the brightnesses of other supernovae that are even farther away. Because they're much brighter, we can see supernovae at much greater distances than we can see Cepheids. And because you can see the expansion of the universe better the further away you look, we look to the far-off supernovae for the ultimate calculation. This chain of brightnesses is referred to as a distance ladder. And you can't move to one rung without first calculating all the ones that come before. Over time, the Hubble telescope clocked distances for several Cepheid variables, the first rung on that distance ladder, which in turn allowed researchers to make an experimental measurement of the Hubble constant. But instead of agreeing with the prediction, it came out totally different: 73 kilometers per second per megaparsec. When experiment and theory diverge, it can mean one of two things: either your measurement is wrong or your theory is wrong. And that, in a nutshell, is the Hubble tension. Which is wrong, the theory or the experiment? That is where James Webb can help. By observing in the infrared spectrum, it will be able to look straight through pesky clouds of space dust that all too often interfere with local astronomers' measurements. The Hubble Space Telescope, the previous tool of choice for local astronomers, has far more modest infrared capabilities. Its infrared measurements come at the expense of lower image quality. But James Webb can do both: observe in infrared and maintain high-resolution imaging. Crisper, dust-free images. That Webb promise. the telescope is such a technological improvement that scientists expect its unprecedented infrared measurements might at last bridge a growing rift between astronomers over how fast the universe is expanding. And in a remarkable observation, the telescope took images of the same stars as the Hubble telescope and calculated a very similar Hubble constant. Although the Planck number disagrees from Hubble and James Webb number by less than 10%, the discrepancy in the measurements implies that there's something terribly wrong with our understanding of the universe. Unless an error turns up in one of the measurements, it will take strange new physics to explain the tension. As cosmologist Adam Rees of Johns Hopkins University, papers in the literature over the last 10 years have invoked anything from weird dark matter to weird dark energy, to another exotic particle, to a magnetic field in the early universe, to a new field, all kinds of things. Some of these explanations look semi-successful, some of them look like failures, some of them would cause other problems. Developing a theory that might resolve the tension is still very much in the skunk works or extremely speculative stage of trying to understand what the tension could mean. Like the Hubble telescope, astronomers using James Webb calculate the Hubble constant by observing flashing stars known as Cepheid variables. As told, combining distance and speed observations of Cepheid stars leads to a measure of the expansion of the universe. But Cepheid variable stars tend to sit deep inside galaxies, surrounded by crowds of other stars. That can make it difficult to get good measurements of the Cepheid speeds and locations. One simple resolution for the Hubble tension could have been that the Hubble telescope measurements were simply off. Enter James Webb, which can peer through the stellar crowds to clearly make out the color and brightness of Cepheid variables. The higher resolution Webb images provide data with dramatically lower uncertainties and reduced confusion with nearby stars than the Hubble telescope could manage. The result? The Hubble telescope measurements have been right all along. This study alone isn't enough to convince astronomer Wendy Friedman of the University of Chicago. The two galaxies studied are comparatively close to us, on cosmic scales, with the farthest one about 75 million light-years away, she notes. The relative proximity makes it easier to pick out the Cepheids from the stellar crowds. Friedman suspects it will be harder to distinguish Cepheids from the crowds of surrounding stars in more distant galaxies, even with James Webb. If so, Rees's confirmation of the higher Hubble constant may crumble with analysis of more distant Cepheids. Hints that the measurements might hold up at larger distances arose in S' presentation at a conference in Baltimore dedicated to the first year of James Webb science. Rees showed preliminary Cepheid data from 4 more galaxies. One of them is 140 million light-years away, among the most distant galaxies in the Hubble telescope Cepheid studies. Webb data from those stars also line up with the Hubble telescope measurements. Although still awaiting peer review, the images strongly suggest that James Webb has indeed overcome the uncertainties that resulted when light from Cepheids got mixed up with light from nearby stars in the lower-resolution Hubble telescope images. University of Cambridge astrophysicist George F. Stathiou, who was not involved in the study, is both convinced that Rees has gotten the measurements right and confounded by the implications. F. Stathiou is a member of the Planck satellite collaboration, which studied the oldest light in the universe, called the cosmic microwave background, and found the lower value for the expansion of the universe. The satellite's calculation is based on images of the patterns in light from the early universe. Together with the standard model of cosmology, the images show that the universe is expanding with a Hubble constant that's lower than James Webb measurement by about 5.6 kilometers per second per megaparsec. As it stands, there doesn't seem to be anything wrong with the Planck measurement of the Hubble constant or with Webb observations. The tension between the measurements points a finger at the standard model of cosmology as the problem. But the standard model also appears to be unimpeachable. it's withstood numerous other challenges without breaking down. The model came about in part due to the discovery of the accelerating expansion of the universe, which earned Rees and others a Nobel Prize in physics. The revelation was a key piece in shaping the model to include dark matter, dark energy, and other factors, making it the simplest theory that can accurately describe the universe. After all, we know that there's still more to learn. This is a crack or a surprise that doesn't fit. Put simply, there's a problem with the standard model. We can revise it, but we don't know how to revise it, which direction or in what way. But note that we also can't rule out the possibility of completely new physics. According to Friedman, if there's new physics, that'd be fun. We'd all like to see something new and interesting. Either way, I think it's going to be an exciting result, either confirming the standard model or showing that there's something still in the model that's missing. Regardless of the final result, scientists still expect James Webb to find it. A silver lining, astronomers observing the galaxy MRG M0138 with the James Webb telescope have discovered a second type UI, a supernova in the distant galaxy. The first supernova was nicknamed Requiem. This second supernova has been called Encore. MRG M0138 is the most distant galaxy to be seen with two-type Ia supernovae, and in fact, that's very important for helping to solve what is possibly the greatest puzzle in cosmology right now. However, there's a catch. While most of the images of the two supernovas have appeared, one of the light paths is predicted to be much longer, based on models of the distribution of dark matter in the lensing cluster. Those finale images are not expected to appear until the mid to late 2030s. While the aging Hubble Space Telescope might not still be active in 2035, hopefully James Webb will still be. If it is, and if it can detect the appearance of the final images from Requiem and Encore, the measurement of the Hubble constant that they provide could help settle the matter of whether so-called Hubble tension is merely experimental error or a real phenomenon. Back on Earth, astronomers have long wondered how Earth became water-rich, bountiful with abyssal oceans, frigid glaciers, and rain that pours from the sky into lakes, rivers, and wetlands. Water, which is composed of the first and third most common elements in the universe, is a deceptively simple molecule to form. However, while the details of its delivery to rocky planets like our own may be essential for understanding life's cosmic prevalence, they remain mostly unknown. Water is a potent medium for the assembly of complex organic molecules and offers havens for the emergence and subsequent evolution of life as we know it. Deep within Earth, it ensures the lithic lubrication that keeps climate-stabilizing plate tectonics from grinding to a halt, another mechanism that just might be crucial for life. And when frozen as ice, it plays a key role in planet formation by providing the glue that helps young worlds grow. As such, scientists are anxious to better understand water's planetary peregrinations, the pathways it takes to transform planets from desiccated rocks into worlds as soaked as Earth. To gain more insight, astronomers are utilizing the James Webb Space Telescope to peer into protoplanetary disks, the swirls of gas and dust around young stars where planets are actively forming today. Although astronomers have glimpsed water within such disks before, their view has been hazy. For example, water vapor is visible to the Atacama Large Millimeter Submillimeter Array, or ALMA. In many respects, the most powerful radio observatory on Earth, but the facility largely cannot detect water ice. This blocks a protoplanetary disk's outer regions from ALMA's scrutiny. The array also cannot deeply probe the hot inner regions of disks where terrestrial bodies form. James Webb, on the other hand, was designed with such studies in mind and has, quite literally, opened the floodgates. The new space observatory is delivering unprecedented looks at how water passes from star-forming giant molecular clouds into protoplanetary disks and finally onto planets. with significant implications for astrobiology, including whether our own watery world is somehow special or commonplace. As Andrea Banzati, a Texas State University astronomer studying protoplanetary disks, said, "With James Webb, it's like suddenly you try on new glasses and they give you a much sharper view." Water's cosmic odyssey began hundreds of millions of years after the Big Bang. That's when the first stars, which had furiously fused through their hydrogen store to churn out heavier elements, burst into supernovae that seeded the universe with oxygen. At this point, a single atom of oxygen could mingle with two hydrogen atoms to form a molecule of water, a molecule that could, in a cosmic cycle of creation and destruction, still be sundered anew by high-energy radiation from stars and other astrophysical sources. But sooner or later, undoubtedly billions of years later in some cases, such water found its way to the cold confines of molecular clouds, where another chaotic and violent chapter of its journey would begin. Molecular clouds are giant, chilly clumps of dust and frozen gas that contain abundant water ice and serve as cradles for stars and planets alike. When part of a cloud reaches some critical density, gravity causes that dense, roughly spherical region to collapse into a flattened, whirling protoplanetary disk with a nascent, glowing star at its center. Much of this process is obscured by dust and has proved almost impossible to probe, until James Webb. It took Webb's incredible sensitivity to enable us to catch the few photons that make it through and hence characterize the icy grains right before the onset of star and planet formation, says Karen Auberg, an astronomer at Harvard University. From there, the growing star feeds on material raining in from its enveloping disk, creating more light and heat, and potentially breaking apart the disk's water molecules to bake off moisture that would have otherwise flowed into worlds. If this process happens too efficiently, the result would be galaxies full of parched planetary systems, and we might well not be here, which is in no small part why most scientists suspect this can't be the case. Somehow, water must pass unscathed from placid molecular clouds through sizzling star-forming disks. In 2021, John Tobin, an astronomer at the National Radio Astronomy Observatory, and others used ALMA to observe V883 Orionis, a disk-wreathed protostar located 1,305 light-years from Earth that is only slightly more massive than our Sun but shines roughly 200 times brighter. The protostar's radiance heats up the frigid outer disk, transforming ice to water vapor that becomes a beacon for ALMA's radio vision. It was a lucky break. Tobin's team saw high ratios of semi-heavy water, in which the heavier hydrogen isotope deuterium substitutes for one of a water molecule's two standard, lighter hydrogen atoms. Because semi-heavy water can only form in cold temperatures, and not the high temperatures directly associated with star formation, its origins around V883. Orionis must date back to the molecular cloud itself, suggesting that the water had passed through the star formation process unchanged. Indeed, the ratio of semi-heavy water to normal water that Tobin and his colleagues observed perfectly matched the proportion observed in other molecular clouds. It also matched the ratio found in our solar system's comets, hinting at one way that water can reach rocky worlds. Astronomers currently think that terrestrial planets can gain water in 3 different ways. It could be that water is there from the start, cocooned within grains of dust that are the very building blocks of the planets themselves. Or perhaps the growing planets siphon water vapor directly from the gas in the primordial disk, allowing gravity to build a humid atmosphere around their rocky core. Or maybe, once the planets have formed, they guzzle water imported via leftover icy debris falling in from far-flung regions of the planetary system. Tobin's results suggest that this latter pathway plays a prominent role, but that water-delivering comets and meteorites do not work alone. Water on Earth has a slightly lower ratio of semi-heavy water to normal water than that found in comets, meaning that while much of our planet's water arrived from the outer solar system's icy hinterlands, some must have instead been exposed to high temperatures near the sun. Just what that exposure looks like, however, remains an open question. To find answers, Oberg wants to build a cosmic map, pinpointing the locations of water around these young protoplanetary disks to see where it is readily available to feed any forming worlds. Alma has already sketched a blurry image, and James Webb is beginning to fill in the gaps with spectacular detail. Last April, Sierra Grant, an astronomer at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, and her colleagues used James Webb to observe water in a disk that had previously appeared dry, demonstrating the Space Observatory's remarkable capability to wring fresh insights even from well-studied systems. According to Grant, we are really in a new era with James Webb. It's remarkable that we could detect things that we couldn't detect before. Then last August, Julia Perotti, an astronomer from the Max Planck Institute for Astronomy in Heidelberg, Germany, and others detected water vapor in PDS-70, the sole protoplanetary disk yet known to harbor not one but two giant planets. Their presence likely means that terrestrial planets are also coalescing within the inner disk, at the precise location where astronomers have now found water. Previous observations had shown no water at all, which was unsurprising, given that water would be hard-pressed to survive the intense radiation so close to the star. Now, astronomers know that it can and that it may just glom onto the atmospheres of planets as they grow, as opposed to reaching dry planets via interplanetary visitors later on. As such, most terrestrial worlds across the cosmos might be born rich, with a wealth of water from the very start. That by itself could be a problem that could lead to worlds that are too water-rich. Scientists currently think that ocean worlds will struggle to create life, but a planet with pond-peppered continents will have much better luck. That's because many of the reactions thought crucial for prebiotic chemistry and the rise of complex chemical systems proceed much more efficiently in small, concentrated ponds than in expansive, diluted oceans. Moreover, minerals that erode from the continents will add crucial nutrients to the water. But to learn how often the universe builds terraqueous orbs like Earth, Oberg argues that we first need to understand young protoplanetary disks by completing that cosmic map, which shows not just the locations of water around these disks, but also how it flows from one locale to the next. Just how water pours from the icy outer region of the disk inward, however, has been unclear, especially in PDS-70, where there is a large gap between the outer and inner disks. Then last November, Banzati, Oberg, and others observed water vapor within the system's snowline, the transitional region, where shifting temperatures transform water from solid to liquid or gas. This confirmed a physical process whereby water migrates inward. 40 years ago, astronomers postulated that water ice in the outer disk would drift inward on sturdier solid material, dust grains and so-called icy pebbles that range in size from a few millimeters up to a few meters, until sublimating at the snowline in a great fog of water vapor. That's the precise signature that Banzati observed, and it has implications for PDS-70. Perotti suspects that this mechanism carried water inward before the gap formed between the outer and inner regions of the system's disk. Or it could be that water continues to migrate through the gap even now, albeit on much smaller, as yet unseen micron-sized icy dust. This dust, along with some water molecules, can act as a protective shield, keeping many water molecules from breaking apart. Oberg's cosmic map is thus becoming more and more detailed, with vast reservoirs found in many regions of protoplanetary disks, suggesting that water may well flow to rocky worlds in myriad ways. But still, astronomers do not know if one scenario has the upper hand. Thus, hope that James Webb's future observations should shed light on the dominant pathway, which might change depending on certain characteristics of the planetary system. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.